You can build corporate security walls 2 feet thick, post guards at every physical entrance, and mandate biometric locks on the server room. But the moment you install a wireless network, your data begins to bleed right through the concrete and hundreds of feet out into public space. This creates a unique conflict. Inside the building, the wireless security architect designs theoretical defenses based on regulatory frameworks. Outside in the parking lot, a penetration tester listens to the raw physical fear space, hunting for a way in. This diagram illustrates exactly where that breach happens. Access points act as critical transceivers. They are the gateways bridging the hardwired internal local area network on the right, with the invisible radio wave environment reaching the remote stations on the left. Because of that bridge, a physical barrier is effectively useless. If an access point projects the network's gateway into a public space, the actual perimeter of the company is out there in the parking lot. This list shows service set identifiers, or SSIDs. This is the alphanumeric name tag a wireless network uses to openly advertise its presence to any device listening nearby. For a penetration tester scanning the airwaves, these name tags are the first target. They specifically hunt for default, out-of-the-box SSIDs. A default name indicates an access point that hasn't been properly updated, signaling a highly vulnerable entry point. In this configuration panel, we see the architect's immediate countermeasure. By setting the wireless SSID broadcast toggle to disabled, the network stops announcing its name to the public. But hiding the SSID is only a psychological deterrent. The network's name might be invisible on your phone, but the raw radio frequencies are still physically pulsing through the air. Securing those waves requires deep structural control. To control the airspace, we have to deal with physical properties. Wireless data is managed by altering the height of a sound wave, its amplitude, and the rate at which it repeats, known as its frequency. These frequencies are then sliced up into specific, manageable channels. Because the space is invisible, radio signals constantly collide. To manage the traffic, networks use a protocol called Carrier Sense Multiple Access with Collision Avoidance. It listens to the channel and mathematically cues the signals so they don't destroy each other in midair. Architects also deploy spread spectrum methods, like direct sequence spread spectrum. Instead of relying on one fragile frequency, the data is distributed across a large frequency bandwidth, making the signal much more resilient against interference. All of these structural defenses are defined by the IEEE 802.11 standard family. As hardware evolves, network architects upgrade from legacy bandwidths to modern, high-density modulation standards, like 802.11ac, to pack more data into the same radio waves. These physics and regulatory frameworks establish the intended rules of the airspace, but these rules operate on a naive assumption that every device in range is playing fairly. Attackers do not play fairly. To see the true physical reach of the network, a penetration tester deploys wardriving techniques, driving through the neighborhood with an antenna, or uses drone-assisted warflying to map the signal from above.
This software matrix shows a diagnostic sniffing tool in action. As the attacker moves, the software quietly logs the exact MAC addresses of the access points, measures the degradation of their signal strength, and identifies the underlying encryption protocols. When the attacker opens the settings panel and integrates their sniffing software with a live GPS feed, the abstract radio signals become concrete. The software pairs the network logs with exact coordinates, generating a physical map of the attack surface. This reveals the reality of the bleeding perimeter. The corporate boundary isn't defined by the building's blueprints. It ends exactly where the attacker's antenna finally loses the signal. To defend the boundary, architects deploy the 802.1x framework, dividing defense into 3 entities: Supplicant, Authenticator, and Authentication server. Traffic from the outside is stopped cold at the access point until the radius server explicitly authorizes it. To verify the server is legitimate, protocols like Protected EAP require a digital handshake. Here is an X509 certificate, which acts as a secure cryptographic passport to validate the server's identity to the remote computer. But a framework is only as strong as its cryptography. Early networks relied on a legacy standard called Wired Equivalent Privacy, or WEP. It was built on a deeply flawed encryption algorithm known as RC4. This interface belongs to an automated key cracking tool used by penetration testers. Looking at the detection status indicators for WEP and WPA, the software listens to the encrypted packets and systematically exploits the mathematical flaws in the RC4 algorithm. Even the most advanced hardware architecture fails if the underlying encryption is compromised.
By relying on legacy standards, the entire network becomes vulnerable to automated computational tools that can recover the shared key in a matter of minutes. This configuration screen shows the architect's required response, abandoning legacy protocols and upgrading to Wi-Fi protected access 2 or 3. Here, we see WPA2 paired with the CCMP 128 AES algorithm, establishing a heavily hardened cryptographic shield. To prevent attackers from injecting fake traffic, the Temporal Key Integrity Protocol introduces message integrity checks. It scrutinizes the sequencing of every packet, blocking active forgeries before they can reach the internal network. But an attacker doesn't always need to crack heavy encryption. If they can't break the math, they manipulate trust instead, using a weaponized piece of hardware known as a Wi-Fi pineapple. Looking at this control dashboard, the pineapple essentially impersonates the company. It broadcasts a rogue access point that perfectly mimics the corporate network. The user's device trusts the signal, voluntarily connects, and hands its credentials directly to the attacker. Because the physical perimeter of a wireless network is completely invisible, defending it requires total vigilance. It demands continuous cryptographic authentication and the complete eradication of legacy standards. Concrete walls can't protect you when your network is always breathing the open air.